Welcome everyone. My name is Keszthelyi and I'm currently a postdoctoral fellow at the University of Amsterdam. In this contribution, I will highlight some interesting aspects of how to get from something like this to something like this. In particular, I will focus on two interesting physical mechanisms which are important to study since they can completely change the properties of the evolutionary models which become red supergiants. Namely, mass loss schemes in massive star models are typically divided at around 10,000 Kelvin, and in the OB phase, the Finckettall rates are commonly used. However, this prescription predicts a large increase in the mass loss rates at the bistability jump, which is not clearly evidenced by observations. Also, the overall rates may be a factor of 2 higher compared to observations. This means that an important revision is needed in evolutionary model calculations. In the meantime, new theoretical mass loss prescriptions for hot stars have been derived, and their impact concerns the mass and rotation of the progenitor models. Here you can see that new mass loss rates in the OB phase allow for higher surface rotation for a given model. This can of course also impact the core rotation of these stars as they become red supergiants. Another open question is how to characterize the evolution of known magnetic OB stars. Namely, a subset of OB stars are known to be strongly magnetized, but it remains unclear what happens to these fossil fields at later evolutionary stages. At the same time, red supergiants show evidence of weak dynamo-generated magnetic fields. On this plot, I show the structure of a stellar model from the OB to the RSG phase. Hot stars can maintain their fossil magnetic fields because those fields are embedded in radiative regions and extend to form a magnetosphere above the surface. However, in red supergiants, we expect large and extended convective zones close to the surface, which would not allow the fossil field to reconnect. Instead, the convective motions could lead to a dynamo mechanism and produce a fundamentally different kind of magnetism. Here I show the evolution of the parameter at a star, which is the ratio of magnetic to wind kinetic energy density. What we predict is that initially strong fossil fields should basically vanish from the stellar surface, but some weak magnetic flux could still remain in the red supergiant phase. In terms of the evolution of mass loss rates, I show here models with and without the effects of fossil magnetic fields. Initially, the winds can be significantly quenched by the magnetic field. However, as the star expands, the magnetic field weakens and the magnetic confinement becomes weak as well. Last but not least, I demonstrate how strong magnetic fields affect the main sequence mass evolution of initially 60 solar mass models. This reveals that a subset of massive stars can experience very minimal mass loss, essentially keeping their initial mass. In conclusion, it is necessary to constrain progenitor evolutionary models of red supergiants. New mass loss rates imply significant changes, particularly affecting stellar mass and rotation. Fossil magnetic fields are observed in some OB stars, whereas dynamo fields seem to take over in red supergiants. This transition needs to be understood.